Hey folks, how's it going? So one of the things I always tell people when they ask about AGI is that when we can consistently get, external displays and conferencing software to work, then we can talk about AGI. So we're a long way from that. I'm still figuring out details here with this external display, but I think because of time limitations, I'm just going to get started. Hopefully things work without the visuals. If something isn't clear, feel free to interrupt, and I'm happy to provide more explanation. So the topic of today's talk is effective transfer learning for NLP, and this is something I'm perhaps particularly well suited to talk about, since that's Indico Data Solutions' primary goal is to enable companies to develop machine learning algorithms with limited amounts of label training data. Hey, how's it going? Yep. Yep. Just a few screen. Feel free to mess around here if you want. And in terms of a rough outline, what we're going to talk about today is first some of the primary limitations of deep learning as it's typically structured, how transfer learning resolves some of those problems that deep learning has, some practical recommendations that we've run across applying transfer learning in practice, a recent tool we've open source called Enso, which is designed to enable people to benchmark and monitor the performance of different applications and different formulations of the transfer learning problem. And then finally, we'll get into the realm of rampant speculation and talk a little bit about some of the more recent transfer learning papers that have come out. In particular, we're going to talk a little bit about the new Elmo embedding language model outputs paper. So first off, what scenarios does deep learning not work well in? So for one, deep learning is incredibly training data intensive. So in terms of training data requirements, you typically don't start thinking about a deep learning solution until you hit something like 10,000 examples. Wow, you're good at this. Thanks so much. Okay, yeah, sounds good. I will point in time immediately. Yeah, I'll give it to you as soon as possible. 10:40? Sorry, 12:40. Sounds good. Thank you so much. That was amazingly quick. Okay, actually, before we talk about the limitations of deep learning, now that I have a visual, let's actually talk about an alternate name for deep learning, representation learning. And I think this is, in many cases, a more accurate term than deep learning to describe one of the primary goals of deep learning, which is to learn to re-represent your inputs in a way that is simpler to map your inputs to a target task. So here we have a really crude drawing of a convolutional neural network on the left. And you can see that the input is fed through a series of layers. At each layer, an activation is produced, and an activation corresponds to a model's representation of what's contained in the image. And here we're looking on the right at a visualization from Visualizing and Understanding Convolutional Networks by Zeiler and Fergus. It's a 2013 paper corresponding with one of the ImageNet state-of-the-arts. And we can see that the features this convolutional neural network is learning are higher level features than simple pixels. So we're looking at things like features that respond to the wheels of cars there on the top left, or it's probably a little hard to see, but on the bottom left, bottom right, we're looking at features that respond highly to pictures of people's faces. So this convolutional neural network model has learned higher level representations than simple raw pixel inputs. And just a quick terminology thing. The thing on the left we're going to call a source model. And in the future, we're going to talk about a target model, which is applying a different classifier on top of this pre-trained classifier to solve a different task. And I gave you a computer vision example, but the same thing or similar things exist in natural language processing. Here's a very simple word-to-vec model, which is a kind of language model where we're learning to represent words by predicting a target word based on its context. So given a sequence of 5 words, in this case, which word is most likely to come next? Or equivalently, given a target word, what context did that word appear in? So in learning to solve this task, we actually also learn representations of the word that have similar high-level meanings to the ones that the outputs or the activations of convolutional neural networks have. So here, this is probably a graph you may have seen before. This is performing simple vector arithmetic on top of vectors learned by word2vec. And you can see that there are these high-level concepts that hold true in this vector space. So you can perform simple arithmetic like the vector for king minus the vector for man plus the vector for woman is roughly equal to the vector for queen. So it's pretty clear that this model has an understanding of what English words mean. So this is what I was talking about previously. Unfortunately, deep learning is not always applicable because of the amount of labeled training data that you have access to for any given task. And it turns out that the tasks that people care about in practice are often highly specific to an organization or to a data set. In addition to having extreme training data requirements, there are also huge training time and computational expense requirements associated with deep learning. So this is a kind of an anecdote from the early days of Enso. We were training our own ImageNet model. We had varied something about the model architecture. I think we had made it a little bit simpler. And about 1.5 weeks into this model training run, someone tripped over the power cord. And there went all of our hard work for the past couple weeks. So we had to start from scratch. And obviously, yes, we should have been saving incremental model outputs. There are a million ways we could have avoided this problem. But it goes to say that the training time required to get an accurate machine learning model, accurate deep learning model out the other end is pretty absurd. It's getting better, though. So there's some really cool papers coming out recently with much reduced training times for ImageNet models. So how does transfer learning address some of these problems that deep learning runs into? Like I said previously, everyone has problems, not everyone has data. Small data problems are much more common than big data problems. And for the purposes of this talk, we're going to define small data problems as anything with less than 1,000 labeled examples. And this kind of order of magnitude is pretty important because it's about the amount of training data a single person could label if they sat down, put on headphones, and had a crack at it. So that's why that data volume is important. Transfer learning, as it means in general, is the application of knowledge gained in one context to a different context. And similarly, transfer learning as defined in the machine learning domain means applying the knowledge gained by one model to another model. So I have another analogy. So if we're going to solve the problem of identifying whether an image is a picture of a tiger or not, yes, of course, we could take a deep learning approach and compile tens of thousands of examples of tigers and tens of thousands of examples of not tigers, and the model would learn to discriminate between the two classes. However, that's not very practical. And our feature representation here, this tiger, naively would be each pixel corresponding to one feature. What a naive model is going to see is something that looks something like this. So this is the tiger image, but I've just shuffled up the locations of the pixels a bit. You can see that a lot of the meaningful structure is lost, and if we're using each pixel as an individual feature, all we can really tell about this tiger is that tigers are generally orange and black, and we can't get a lot more structure out of it than that. However, if our features, instead of being pixels, were high-level concepts like how large is the thing in the image, how orange is the thing in the image, how striped is the thing in the image, how cat-like is the thing in the image, you can see that this task of learning of whether or not something is a photo of a tiger is much simpler. A person might only need a couple examples of tigers to understand that, hey, look, high activations for each of these features corresponds with this image containing a tiger. And that's the fundamental concept of transfer learning. It's re-representing these inputs in a more meaningful, higher level representation. In practice, learned features aren't always this interpretable, so you don't get a feature out that literally corresponds to orange or literally corresponds to how cat-like the image is necessarily. But the relationship between the input features and the target, whether or not this is a tiger, is much simpler. And learning simpler relationships between inputs and outputs requires less training data and less compute power. So here's kind of a diagram of probably the most basic formulation of the transfer learning problem. First, you train a base model on a large generic corpus. Secondly, you compute what that model thinks of different input data for a different task. And thirdly, you train a lightweight model on top of these pre-trained feature representations to solve a custom task. So visually, it looks something like this. So there on the left, with the parens, we have a shared encoder or a featurizer. This is what we're going to refer to as our source model. And let's say this is trained on a task like predicting movie review sentiment. And there on the right, we have several different custom classifiers that each use the same feature representation that the source model produces to solve a variety of custom tasks, like predicting the genre of the movie, predicting what aspects of the movie review express sentiment, or perhaps what the box office results of the movie in question is. So again, to summarize, how does transfer learning fix deep learning's problems? A, computing pre-trained representations means that we have simpler mappings between inputs and outputs. We can use simpler models, and we require less training data. The memory requirements are actually much, much lower than those of deep learning. If your feature representation is smaller, you need fewer parameters in order to learn a relationship between input and output, and therefore you can actually save this target model in a file that's the size of kilobytes rather than gigabytes, like is typically required for deep learning models. You have thousands rather than millions of parameters. And your training time is typically measured in seconds rather than days. What does this application look like in practice? If you follow HBO's show Silicon Valley, you might be familiar with the Not Hot Dog app that actually corresponds to a real application on the App Store. I actually haven't gotten this far in Silicon Valley, so I don't get my own reference, but pretty much what I've been told is that as part of the show, one of the engineers builds an application to detect whether or not an image is a photo of a hot dog or not a photo of a hot dog. And the person who built this in real life only required a couple hundred examples of hot dogs and not hot dogs rather than many thousands examples. However, transfer learning for natural language processing has its complications. For computer vision, this has been very well proven, and people have already been applying this for quite a long time. But natural language processing, there are more varied target tasks. So you might be trying to do something like labeling the part of speech of each word in a sentence, or classifying a document, or extracting named entities from a document. These are very diverse task types. There's a larger amount of variety in the input data to a model. So natural language processing models might have to deal with variance in the source language used. They might have to deal with field-specific terminology. A model trained on financial reports is not going to perform well if it's applied to the biomedical domain. Whereas the components that make up computer vision features are more generic. They work better across different scenarios. There's no clear equivalent to the ImageNet dataset. This giant dataset of a 1,000-way classification problem doesn't really have a counterpart in the natural language processing domain. So we're kind of missing data fuel to make this work well for natural language processing. And there's a lack of consensus on what kinds of tasks are good to solve if you want to learn generic representations that work well across target tasks. So, because we've been doing this for quite a while at Indico Data Solutions, we can make a couple of practical recommendations for you how you can actually see these benefits in your own work. A, whenever possible, make sure the task and the vocabulary of your source model is aligned with your target model. The thing we found in practice is that the quality of your source model, not necessarily how well it performs on the task it's trained on, but the quality of your embedding is the single most important variable in whether or not you're able to make a transfer learning use case work. So in order to evaluate whether or not a source model is a good feature representation for a different target task, you should look at the vocabulary, the kinds of words that appear in that corpus, and compare it to the target corpus. You should look at what kind of task is being solved and ensure that that kind of task aligns with the task that you're trying to transfer to. So some examples of good use cases might be taking a model trained on a product review sentiment task and applying it to product review categorization, or taking a hotel rating model and applying it to restaurant ratings. In the first one, we have similar corpus, different task. In the second one, we have similar task, different corpus. Less good would be doing something like product review sentiment to biology paper classification. And here on the bottom, we just have a visual analogy. You're pretty much looking to match attributes of your model and data set across your source model and your task model. So what source tasks produce good general representations? So here are tasks that generally produce representations that are applicable across many different target tasks. I'm pulling from recent machine learning literature for these, so papers that have appeared on arXiv over the course of the past year. One task that's shown good results is the task of natural language inference. So this is the task of comparing two sentences and saying, are these sentences similar? Are these sentences dissimilar? Or are they just entirely unrelated from each other? The task of translation requires a very good understanding of the content of text. If you're able to translate a document, you sure as hell better know what's contained in the document. You better have a pretty good understanding of what the English text is trying to convey. Multitask learning is a very clear win here, because training a source model to solve many different supervised problems at once probably means that if the model is given a new supervised problem, it's applicable to that problem as well. Those features can be reused. And finally, language modeling, the objective or the source task that I'm most excited about. Language modeling is learning to model the natural distribution of English language, i.e., given some context, what's the likelihood that each word will appear next in your vocabulary. And this is an entirely unsupervised task, so you don't need labeled training data to train a language model. And because of that, if you have a large amount of unlabeled data and a very small amount of labeled data, you can see benefits. Keep your target models extraordinarily simple. When you have less than 1,000 examples, there is no need to overcomplicate the complexity of your target model. Logistic regression honestly goes a very, very long way. We'll show some actual results here in a bit. And regularize your models well, because when you have very small amounts of labeled training data, the tendency to overfit is pretty extreme. So use L2 reg or dropout. Here's just kind of a visual of what overfitting might look like visually. Instead of learning a very simple relationship between your inputs and your outputs, you're learning an overly complicated representation of your inputs that doesn't necessarily correspond to something that's going to generalize to data you haven't seen yet. Consider using second-order optimization methods. So you may have heard of a technique called LBFGS. This approximates the second derivative of a loss surface at any given point in time. But it's generally overlooked in deep learning literature because it's very sensitive to the number of parameters and the number of examples you have in your data set and your model. However, it's an excellent fit for transfer learning applications because the models you're training are typically very simple. They are typically parameterized by a very small number of parameters. And therefore, second-order optimization methods work quite well in practice for transfer learning applications. If you want a sense of what this looks like visually, most SGD-based methods are computing the derivative and moving in the direction of the derivative, whereas LBFGS is computing the curvature and the derivative at any given point and moving towards the minima of the local curvature. When you're comparing different approaches, make sure to measure the variance of your approaches as you look at different CV splits, different cross-validation splits. Because you have a very small amount of labeled training data, you have even less validation data to use, which means that the variance of your model performance may be very high. And high variance in performance generally corresponds with overfitting behavior and corresponds with models that are not going to generalize well to new input data. So monitor that closely and prefer methods that have low variance in the results. Pretty much every single one of the classic machine learning problems or pitfalls is exaggerated at small training data set sizes, like I've just kind of explained here. So class imbalance, for instance, can be extremely problematic in a transfer learning case. If, let's say you have 10 examples, 9 out of those 10 examples appear and they have the same class label, it is very trivial for your model to get gains in terms of lowering the loss of your objective by simply predicting the most common class. And when you have more training data, it eventually becomes valuable for the model to do something other than predicting the most common class. if you do not have very much training data, predicting the most common class is absolutely an effective way for the model to see a decrease in the loss. So be very careful about oversampling and undersampling. Make sure you provide a model with class-balanced representations of your data if you want to learn anything informative. And the same is also true for things like spurious correlations. Let's say you happen to label data that all came from the same day. If some major national event happened on that day, the model might learn an association that isn't necessarily a useful association. So just be very careful about the source of your input data to the model. If you're going to label 100 examples, make them 100 good examples. And also, perhaps this is an unpopular recommendation, but feature engineering absolutely has its place. Modern day feature engineering often looks like changing a model architecture or changing the inputs to a model. You're still taking advantage of pre-trained representations, but you might apply some transformation to them to make the mapping between your input data and your target task more intuitive. So for example, a recent problem we ran into was the problem of matching resumes with job descriptions. One way to formulate the input to the model might simply be to concatenate the representation of the resume with the representation of the job description and ask a model to learn whether or not they're a good match for each other. But when you have a very simple model, like logistic regression, it's very difficult to learn this relationship. So a very simple transformation where you literally subtract the representation of the resume from the representation of the job description and look at the absolute difference of the two makes this task drastically simpler for a model to solve. So think about ways you can manipulate your inputs and use your own domain knowledge to make the task simpler for a machine learning solution. And actually, more and more, I think people are realizing the value of having domain expertise when training deep learning algorithms or training machine learning models in general. DeepMind in particular, there's a tweet I read this morning that said, most of the success of DeepMind, or a large part of the success of DeepMind, is in pairing domain experts with deep learning experts and having them work on very particular problems. That's where you see real benefits. So in order to effectively evaluate what approaches worked well, we actually built our own framework, which we call Enso. Enso is a standard interface for the benchmarking of embeddings and transfer learning methods on natural language processing tasks. The goal here is kind of to help avoid human overfitting of hyperparameters to values that work well on singular tasks. So one thing that can occur if you're always evaluating on the same data set, and you keep tweaking your model parameters, adding more layers, eliminating layers, changing regularization values, eventually you might just happen to stumble upon values that work well. But there's no indication that this setting is going to work well on a different task. And you may have happened to stumble upon some association, some relationship that doesn't actually exist generically or more generally. So evaluating across many tasks helps avoid this human overfitting of hyperparameters. We want to ensure that baselines are higher fidelity. Oftentimes, an easy way to get a paper in a journal is to benchmark against a bad baseline and show a huge improvement. We don't want that to be the case. And benchmark on many data sets to better understand where an approach is effective. One of the things we've seen doing this a lot in practice is that very few techniques work across the board. They're applicable to certain domains, they're applicable to certain problem types. And you should understand which techniques work where in order to better use those techniques. What does the workflow look like? First, in plain English, out of the box, you can download 24 included data sets to benchmark on top of. You can call a command to featureize all the examples in your data sets via any pre-trained source model. You then train a target model using those featureized inputs. And you repeat the process for all sorts of combinations of featureizers, data set sizes, and target model architectures. And finally, we have a tool built into Enso to visualize and manually inspect the results to see what worked and what didn't work. In code, looks like this. So like I said before, at under 1,000 examples, very, very simple techniques work extraordinarily well. So it's going to be a bit hard to see, but the two lines, the light blue and the red line at the top, are simple logistic regression. We're comparing it to perhaps slightly more complex models like support vector machines that have a larger number of parameters, some more flexibility to work with. We're also comparing two different featureizers here. So if you're familiar with Spacey, a natural language processing toolkit for Python, Spacey provides two different out-of-the-box featureizers, one which is based on glove word representations and one which is based on a convolutional neural network's output on top of word embeddings. And we found that in our case, the difference between the two was minimal. And that held true across most tasks. There are a couple tasks for which the CNN performed much better, but like I said, very few tasks, or very few improvements work generically. So understand where things do work and where things don't. And like I said previously, the red line on top here is the application of the LBFGS optimizer as compared to the application of SGD. Here, the different plots correspond with different metrics that we're keeping track of. So things like ROC-AUC scores, accuracy metrics, precision recall. We want to give you a very detailed look at what model changes, what source model changes produce what kinds of behavior and what, how they impact the results. And it's documented and available online at github.com/indicodatasolutions/Enso. And the documentation is available at enso.readthedocs.io. Yep. I'll let you take a photo or write that down if you like. And contributions are absolutely welcome. Right now, we only support classification tasks, but we want to branch out to things like sequence labeling and things like comparing two documents, tasks that require determining relationships between different documents. If you're familiar with cent-eval, this is kind of an alternative to using cent-eval for benchmarking a new source model or a new target task. And finally, we're going to move on to some very recent machine learning research. I've highlighted a few of the papers that I think are good papers for better understanding the current state of transfer learning for natural language processing. Most of these papers work or operate in domains where there are more than 1,000 labeled examples available, but they're still interesting to look at. The first of which is learning general purposes distributed sentence representations via large-scale multitask learning. This is something I talked about previously. If you train a source model with many different objectives, many different tasks, you find that the embeddings it learns generalize better to a wide variety of tasks. And there's also paper called Fine-Tuned Language Models for Text Classification that takes an entirely different approach to transfer learning than what we're explaining here, where the source model is not fixed. In fact, you're modifying the source model's weights in order to make the model more effective at solving a given task. And they provide some practical recommendations for how you make this work in practice. That include how you vary learning rates per layer, how you modify some LSTM losses to get a bigger advantage out of a smaller training set. And finally, the paper I'm going to focus on over the course of the next couple slides, a paper called Deep Contextualized Word Representations, that we've actually seen very good empirical results for using the representations learned by this paper. And it's a paper out of the Allen AI Institute that comes very highly regarded. The basic premise of this paper, Deep Contextualized Word Representations, is that A, language modeling is a great objective for a source model that is intended to be used for transfer learning applications. B, it's not just the final layer of representation that is useful in solving a target task. Each of the layers of representation varies in its usefulness depending on the target task that you're looking at. So this is actually what the plot at the bottom here is showing. This is a bidirectional LSTM. We learn input representations of your tokens. We learn an output representation of the forward LSTM, and we learn an output representation of the backwards LSTM. And then a model applied on top of this model learns how important each of these layers of representation is for solving an end task. So you can see it varies wildly across each of these different target tasks. Some of them depend only on the outputs of the forward LSTM. Some of them depend pretty strongly on the input word representations. And learning per token representations rather than a simple representation of a document as a whole means that you get applicability to a broader range of kinds of target tasks. So it means that these embeddings are appropriate for doing things like labeling the part of speech of words, or determining whether or not a word is a named entity, as part of a named entity. Here's another visual representation of this process of learning different feature weights per layer of representation in the source model. So you have the input represented in orange and 2 hidden states represented in blue and light blue. And we learn different weights for each of them to average this vector into a single representation that's used by a target model. And importantly, these all have to share the same dimensions so you can actually perform an average. They used a bidirectional LSTM, which has been and continues to be pretty much the go-to for language modeling. Although there are some competitors now, like CNN-style models with dilation and transformer architectures. This is an image from Chris Ola's personal blog. If you're not familiar with distill.pub, I highly recommend you check out distill.pub for beautiful visualizations of a lot of machine learning concepts. And instead of simply applying a logistic regression model or other simple classifier on top of the representations learned by the source RNN, they actually train a task RNN on top of the output representations of the source RNN to solve a given task. And here on the right, I'm going to blow this up. Instead of actually, because we have very limited amounts of training data in the domain that we care about, we went ahead, we took these average representations and we averaged them across token representations as well, and we saw good results when compared to the accuracy of a model only using glove vector representations. So it's an expensive to run model, but more than anything else, this was one of the variables that mattered quite a bit. So the red line is the Elmo embedding, or the learned embedding of this LSTM, and the blue line is a mean of glove vector embedding. So sorry if that was a bit of a whirlwind. If you take nothing else away from this conversation, know that small data problems are way more prevalent than big data problems. Almost no one we come to has labeled training data. We have to get them there from the very beginning. Transfer learning enables you to take advantage of labeled training data you have from other domains and apply it to a different target task. And when in doubt, trend towards simplicity. There's a lot of hype out there. Try and cut through the hype. Start first with the simple baselines, especially when you don't have a lot of labeled training data. The simple things go a very long way. So, yeah, thanks. I think we have a little bit of time for questions.
Thank you, Madison. Questions?
Yeah, up front.
Hold on.
Thank you for a great talk. In machine vision, when applying transfer learning, there are a couple of principles that tend to help a lot, like making sure that you're don't try to redo ImageNet, right? Don't classify across 1,000 possible categories if what we're trying to do is do it with just like a few hundred examples. One of the things that makes it work better is if you only go for a few classifications versus many. And another finding is that transfer learning can produce results that are competitive with building the model from scratch if you actually had larger data, right? It takes away the advantage of large data. Could you comment on those two factors as it relates to doing this for NLP work, classification, in transfer learning domain?
I would say for the most part the exact same thing holds in that, but I think this is just something that applies to machine learning in general. Formulating a simple problem for a model is going to be more effective than formulating a complex one. Some of those problems have to do largely with the metrics people care about, in that it may appear that less meaningful relationships are learned by a transfer learning model if there's a large number of target classes that you care about. But part of this might just be the simple fact that as you increase the number of classes, the problem becomes more complex. And even with a large amount of labeled training data, you'd see the same problem that the performance of the model attenuates as you increase the number of classes you care about. I think perhaps a bit more than computer vision, training a model from scratch does offer a bigger advantage at the upper limits of training data volume. But I can't comment on that as much as I'd like to. So,
well, could you comment on the spread that you've seen in the models that you've run of doing transfer learning for NLP versus building from
so
scratch?
for most of the tasks we care about, we simply don't have a large labeled training data equivalent. Okay. So it's very hard for us to run a comparison because there's no other option. There's no alternative. So we don't have as many data points as I'd like to.
Right, fair enough. Thanks, man.
Yeah. How's it going? Yep.
Hi. Could you share with us examples of source models and data sets that are available to the public and that have been useful for you?
Yep. So at the most basic, people usually start with using the average or some sort of smooth weighted average of word to vect or glove models. Those are freely available to the public. The Elmo model is also openly available to the public, so you can look at Allen NLP. That's a Python package you can download. They ship the model weights along with their model. It's expensive to run, but the features output are very, very informative. So I would look at all three of those. In addition, I would encourage you to consider training your own models if you can find a good proxy data set. And use best practices. LSTMs get you a pretty long way there. Yeah, the better the alignment between source and task model, the better performance you're going to get.
Hi. I was wondering if you have any other examples of feature engineering for small amounts of text?
Yeah, another example might be you're given a document as a title and has several different sections in the document. You might concatenate the representations for each one of the sections of the document or produce a feature representation that you feed into a model. The comparison is probably comparison example where you're trying to compare two things. It's probably the most common example we see. You also might consider things like some of these we're using a mean of embeddings versus a max of embeddings or the last state of an LSTM. Different things make sense in different contexts. For instance, if you're looking at some sort of detection problem where you have a very, very long document that contains a lot of irrelevant content and only a small section of the document contains the thing you care about, you might consider a max operation rather than a mean operation. Yeah.
The Elmo architecture.
Yeah.
And it wasn't clear to me. Could you explain, are they using the original input and the feature embeddings as one whole thing for transfer learning?
Yes. So they're using a learned average of the token representations that the model learns, the Elmo model learns, the first forward LSTM output activations, and the backwards LSTM output activations. So these all produce a feature vector that's length 1024, and they learn to weight each of these and feed them directly as inputs to the secondary task RNN. Is that anything else there? Is that
No, that was the question. Thank you.
Awesome. Anyone else? Yeah. Yeah.
I could grok why if you were, if you have a small amount of data, why stacking a logistic regression on top could work and why you wouldn't run into overfitting problem. But once you introduce an LSTM, it's a lot more complicated. So
yes. They evaluated larger training data set sizes than we are in Enso.
How much larger?
I want to say a factor of about 10. So it's not as bad as you would expect. But
so about 10,000 samples versus about 1,000 samples. Cool. Thank you, man.
Yeah.
Yeah, so a lot of these pre-trained models, they work on generic English languages, right? And then you're trying to do some kind of task related to that, then that's fine. But if you have a requirement of a domain-specific language, like you're working on a telecom domain or a customer domain, right? So they, and you have to use some of the English quality of like the pre-trained model, but then add onto it the domain-specific language intelligence, right? How do you come up with the embeddings? Like, how do you go with this using the pre-trained? What do you customize? Where do you?
You customize the way in which each of the features of a model trained on a different domain is weighted in terms of its value to predicting the target task in a more specific domain. At least that's a formulation when you feed it into a logistic regression model. You might also see success if there are other labels present in your domain-specific context that you do have readily available. Let's see, that's a good example. Let's say you have a customer support data set, I think like you mentioned, and you have a data set of which customer support engineer handled a given ticket or a given conversation, and you have many, many hundreds of thousands of these examples. You might train a model on that task and use the representations learned by that model, which understands this very specific language from this domain, and apply that to something like a customer churn prediction model. So the best source models are the ones that are most closely related to your target tasks.
So what you're saying is the pre-trained like Word2Vec or they won't work in this scenario?
I think they would work fairly well, and I would absolutely recommend benchmarking first with those models.
Okay.
Because it's diminishing returns, right? Usually the simplest techniques get you 80 or 90% way there, and the rest of it's fighting for that last 10 or 20%.
So it's kind of more of a hybrid model in that case, like that model, and that gives input to that model.
Yeah. The other thing would be if language modeling does turn out to be very good objective for learning good representations of documents and words that work well in transfer learning scenarios, then you really don't need labeled training data in the target domain or in the domain you care about. All you need is unlabeled training data. So you can learn to model the natural distribution of that domain language. And that's an objective that's good enough in itself. Yeah.
Are there any tricks to handle new named entities that come about, which will always happen?
So like domain shifts, like meaning the...
Even in the same domain, just, news, for example, right?
News. I can't make good recommendations there. I wish I could, but I'm not as qualified to speak about that, unfortunately. But yeah, that's very related to the transfer learning problem. You know that your data distribution is going to shift over time. You should be able to account for that. Look up domain shift. Should give you some information there.
The metadata of that named entity, what type it is, category, if you had a knowledge base to look it up.
Potentially, I'd have to think about it a bit more. I would say, for the most part, my recommendation would be to retrain the source model so that it has knowledge of those entities. And that's obviously not practical to do all the time, but you'd certainly get better representations of new entities out the other end. So expensive, but maybe functional.
Typically, people just skip it if they encounter something out of vocabulary.
Oh, if you see a word you haven't seen before, yeah, you typically replace it with an out-of-vocabulary token. It's either a zero vector or the mean vector of all the other tokens. Yep.
Thank you.
No problem.
Okay. Cool. Thank you, Madison. It's lunchtime, ladies and gentlemen. Enjoy.
Thanks so much.